So alright, before we start this subsection, do we have any questions? So now here, let's talk about the general one-dimensional analysis. Okay, here the step of analysis. So I tried to fix my camera, during the break, but it didn't work. I don't know what's wrong. So this is step of analysis. Let's consider first we have to idealize the problem. So first we need to consider, we need to check what's the boundary condition. So make sure that there are two different kinds of boundary condition. Boundary conditions. in 우리말 경계 조건. So first one is displacement boundary condition. 변이 경계 조건. The second, so false boundary condition. 하중 경계 조건. Okay? So let's consider here. So first we need to identify the point where we want to measure the nodal displacement. So I didn't like to measure the nodal displacement A at B and C and also at D. And then if I check the boundary condition, so I told you that we have always two different kinds of boundary conditions. So at point A, so we have reaction, but reaction is not known before any calculation. That's why instead of any force boundary condition, but we know that the point A cannot move because of the support. That's why this is the displacement boundary condition. Here, any displacement at point A is equal to 0. And then how about let's look at point B. Point B, instead of displacement, the load is given here. Here we have load boundary condition, the force boundary condition. At point C, also we have force boundary condition. At point D, we also have force boundary condition. Okay, so here we want to consider 1, 2, 3, 4 nodes. And then this guy is subjected to the displacement boundary condition. These three are subjected to the force boundary condition. Okay, so once you recognize the displacement boundary condition and the force boundary conditions, then the next step is we need to introduce a coordinate system. So here, so what kind of coordinate system you want to use? So let's say we want to use this coordinate system. So downward is positive. Okay? And the third step, we have to define the nodal points where to measure the deformation. So I already did. I want to choose only 4 points. Okay, 4 points. And then we need to define the displacement vectors at the nodes. So this guy at the step 4, hinges on the choice of coordinate system because the downward direction is positive. That's why UD is downward, UC is also downward, UB is downward because we didn't calculate it yet. UD and UC, UB. Sorry for this poor writing because I am using my mouse, that's why. And then fifth step, we need to calculate the elongation. So look at this. So please keep in mind this diagram, stress and strain and displacement. Okay, so we can do our analysis from the force and the stress and strain and the displacement, or we can start from here. We can start from the displacement. Actually, this is my preference. I like this direction better because this is more general. So maybe I can explain you the reason later. We need to consider the nonlinear behavior. Anyway, this is more general, okay? First, we define the displacement field, and then we calculate the corresponding strain and the stress, and we finish our analysis checking the force equilibrium. Okay, so let's consider this problem. And then I have UA, UB, UC, and UD. So let's calculate the elongation. So elongation in AB segment is calculated as what? UB minus UA. Here UA is equal to 0 because of boundary condition, simply UB. The elongation in BC segment is calculated as UC minus UB. So make sure that it's not UB minus UC. So of course you choose upward coordinate system, then in that case the elongation is UB minus UC. And then the elongation of CD segment is measured as UD minus UC. Is it clear, right? So we just calculate the elongation. So in the middle of this arrow. So next step, I want to calculate the strain. The strain, here we are here. Strain in AB segment is equal to what? By the definition, the elongation in that segment divided by the length. Here the length is given by L1. And this is equal to what? UB divided by L1. So make sure that here UB is not a vector, okay? This is not a vector. Here UB represents the magnitude of the vector, okay? So as I told you the last time, to form a vector, we need the magnitude and also the direction, okay? And then strain, strain in BC segment is elongation of BC segment divided by L2. Isn't this is more systematic, isn't it? UC, UB, L2. Look at this. We just calculate the elongation here. And the strain in CD segment is equal to elongation in CD segment divided by the length. This is equal to UD minus UC divided by L3. Isn't it clear, right? So we are here now. So we are here. We just calculated. We started from the definition of deformation field. And then we just calculate the strain here. Then what's the next step? We need to calculate the stress value. The how? We want to use the Hooke's law. This is really straightforward. The stress of AC segment is elastic modulus of that segment. So in this problem, for simplicity, I want to consider the same material is used. The elastic modulus is constant from from point A to point D. Elastic modulus times the strain of that segment. This is equal to what? E L1 UB. And then BC segment is equal to, by the same logic, this is L2 elastic modulus UC minus UB. And then, stress in CD segment is equal to elastic modulus L3 UD minus UC. Okay, so we just finished the calculation of stress. Okay, we just calculate the stress distribution. So now the next step is I want to consider what? the force equilibrium for individual segment. So now let's work for here. Let's consider this free body diagram. So if you consider this free body diagram, then I have force P at point D, and then I need to consider the stress in CD segment. So here, to consider the distribution of stress, we must have two different options. The direction of the CD look like this, or downward direction. This is option 1 and option 2. So which one is correct? By the way, we are here now, okay? So we calculated the elongation, we calculate the strain, we calculate the stress. So now we are calculating internal forces. So which option is correct? Option 1 and option 2. Can you give me the answer? Option 1. Eugenie, can you explain why you think option 1 is correct one? So make sure that the sign convention of stress is what? If the stress stretches the material, then the normal stress is positive, isn't it? That's why this direction stretches the material, okay? And this direction is what? That compresses the material. So that's why we want to choose this as default one, okay? Alright, so if you do that, so for this, we can consider the force equilibrium. So I want to consider any local coordinate system. So let's check the force equilibrium for this. The sum of all the forces in the vertical direction is equal to 0. So here it follows the positive direction, sigma CD, and then the cross-section area. So I want to consider same cross-section for simplicity. And then according to this local coordinate system, the external force in the negative direction, minus direction, so PD, is equal to 0. So here we can easily conclude that sigma CD is equal to PD divided by A, okay? Now, here, let's consider this. So elastic modulus and area, and then L3, the UD minus UC is equal to PD. So we get the first equation. So let's consider another free body diagram. So let's consider this free body diagram here. Okay, so let's consider this free body diagram. So in the second choice of the free body diagram, so we have external force PD here, and then I have another external force PC here. Then my free body diagram crosses BC segment. So here we have to consider the distribution of traction in what segment? BC segment. BC segment, isn't it? So let's do the same thing. Okay, so last time we used local coordinate and upward is positive. So I want to choose now in this time. It's okay, downward is positive. So any calculation is okay. So here, any forces in downward is equal to 0. So because here this is minus, isn't it, right? The minus direction according to this. So minus sigma BC times the area plus PC and PD is equal to 0. So if you move PC and PD in the minus sign, that's why from this equation, if you call sigma BC here, elastic modulus and cross-section area divided by L2 UC minus UB, UC minus UB is equal to PC plus PD. Is it clear, right? Okay, so I got the second equation. And then let's check another free body diagram. Let's consider this free body diagram. So make sure that here, at this point, so how many unknowns do we have? Because UA is equal to 0, that's why UB, UC, and UD. So we have only 3 unknowns. Then to calculate the 3 unknowns, we need 3 equations. We just got, first and second equations. We need 1 more equation. That's why I want to consider this free body diagram. So if you consider this, then I have force PD, and then PC here, and then I have PB, isn't it right? PB upward, and then here we need to consider distribution of normal stress in AB segment. Okay, so now let's choose the local coordinate system in this way. Sum of forces in upward direction is positive, is equal to 0. And then this is sigma AB times the cross-section area plus PB minus PC, because of the the choice of coordinate system, minus PD is equal to 0, isn't it? So let's consider this. Let's move all the forces to the right-hand direction. Then, so we can obtain the formula, the last formula, because sigma AB is already calculated in this way. Elastic modulus times cross-section area divided by length and L1, and then UB, isn't it? Let me check. Yes, correct. UB is equal to PC plus PD minus PB. Okay? So this is a third equation. So can you calculate out UB, the nodal displacement UB, from this equation? Because there is only one unknown and one equation, so we can calculate the UB. Then once we calculate UB, and then you plug UB here, then we can calculate UC. Okay? So once I calculate UC, let's plug UC into this equation. Then we can calculate UD. So now we calculate all the nodal displacement. So can you calculate the strain? Yes, we can calculate the strain, because now we have the nodal displacement values. Here make sure that UB and the UB and UC and the UD and UC, using this nodal information of the nodal displacement, I can calculate the strain in AB segment, BC segment, CD segment. So once I have the information of the strain, so let's put the strain into here. Then we can calculate the stress values. Is it clear? It's very easy, isn't it, right? Do you have any questions? Okay, so once you finish the analysis, then we can plot the distribution of actual force. This is called actual force diagram. Okay, actual force diagram. Simply we call AFD. AFD. So we'd like to plot the internal forces. Okay, we'd like to plot the internal forces. And then also we can put the actual displacement diagram. Please note that we calculate only nodal displacement. This is support is equal to 0. This is a displacement at point B and point C and point D, we calculated only the nodal values of the displacement field. Now how about in the middle of the two nodal points? Because we consider homogeneous and the straight bars, and the change should be homogeneous. What I mean, the strain is constant. That's why we can draw a straight line connecting these 2 points. Okay, that's why we have the distribution of actual distribution of actual displacement. Okay, so now let's consider a simple example. So first we need to identify the force acting at point B. Then because we have force P, so we can easily calculate the force acting at point B. Then this is equal to what? The PB is equal to, it's very easy, right? Because of the sum of moment at point with respect to point D is equal to 0. So A divided PB, sorry about it. B divided by A. It's not minus sign, okay? A times PB, P2, sorry. Okay. So let's check if you calculate anything, you do better to consider the extreme case. Let's consider if B is very small, if P2 is very close to D, then because of the leverage effect, the PB should be very small, isn't it, right? Should be proportional to the length B. So let's consider B is almost equal to 0, then our PB is also equal to 0. So we can check our calculation indirectly. So now let's focus on this one-dimensional problem. Okay, so now we have one-dimensional problem. So I have let me check my OBS. Then I have a support as a simplification, and then I have A and B, and here C segment, the C point, and then I have these members. Okay, so exactly one-dimensional problems. Here we have load PB. So PB is equal to, given by BA and then P2. So what's the length of A? A is 28 inches, B is 25 inches. That's right, 25 inches and 28 inches. How about P2? P2 is 5,600 pounds. 5,600 pounds. So make sure that B, the unit of B is cancelled by unit of A. That's why we have unit of force, the pounds. Okay. And how about load P1? Here we have P1. So P1 is acting on PC. What I mean, node C. So I want to call this is PC for any unification. So P1 is given as 2,100 pounds. So all the numeric values are given here. And then how about the length? L1 is equal to here 20 inches. And then how about L2? So L2 is, let's check in this example, 34.8 inches. Okay. And how about cross-section area? Cross-section area A1 is 0.25. So AB is 0.25 inches square. And then here BC is equal to 0.15 inches square. Is it clear, right? So now we are ready for our analysis. So the very first step that we have to do is what? We need to introduce a coordinate system. So I want to introduce this coordinate system. This is default positive x. Okay, so now let's prepare a chart. So nodal displacement and then x coordinate. That corresponds to point A, and then we have point B and then point C. So make sure that point A is fixed. This is the boundary condition. It is supported. So that's why the nodal displacement at this point should be equal to 0. So at point B, we must have non-zero nodal displacement. This height is equal to UB. And also at point C, we have nodal displacement UB. The distribution of displacement field look like this. As I told you, so because we want to consider homogeneous problem, homogeneous materials, the slope is always constant. Okay? So, and then, so in my map, the displacement and strain and stress and the force. So we just identify the deformation field. So next step, we need to calculate the strain, isn't it, right? So now let's try to calculate the strain. Strain is what? Strain is given by this slope. So elongation in this segment is UB minus 0 and UC minus UB, isn't it? So this is 1 and this is strain. Strain an AB segment is equal to UB divided by LAB. So LAB is L1. Okay? And then here the strain BC segment is given by L2 and then UC minus UB. Is it clear? So now we are here. Okay? We just calculate the strain field. So can you calculate the stress? Yes, the calculation of stress is really straightforward. Stress in AB segment is what? So in this problem we have, where is elastic modulus? Here, elastic modulus is given here. Elastic modulus of the steel is given by 29.0 times 10 to the power 6 psi. The elastic modulus of strain, the AB segment. Okay, so numeric value is given here, so that's why I don't want to write here. And then sigma BC segment is also elastic modulus times strain BC segment, isn't it, right? So if you do that, stress in AB segment is equal to elastic modulus L1 and UB. The sigma BC is equal to elastic modulus L2 UC minus UB. Okay? So now we are here. Okay? We are here. Then what's the next step? The next step is we need to check the force equilibrium. So let's consider free body diagram. So we can do one by one. So let's consider this. So if you do that, so I have PC, and then the stress distribution on this cross section is equal to sigma BC. So let's check the force equilibrium. Then we can easily recognize sigma BC times the cross-section area of the BC segment, so A2 is equal to PC. So let's plug in the information of sigma BC here. Then UC minus UB is equal to L2 elastic modulus area and then UC minus UB. Here, sorry. I meant mistake. UC minus UB times PC. So I have an equation, but I have two unknowns. That's why we cannot finish the calculation. So let's consider one more the free body diagram. Let's consider another free body diagram here. The rule of equilibrium must be satisfied to any point of this this structure. Here, let's consider here. So if you do that, I have PC and then PB. So make sure that the numeric value, we already have their numeric values. It's sigma AB. So we can do the same, okay? We can do the same. The sigma AB times cross-section area at that point is equal to PC minus PB. It's trivial. The calculation is really trivial. So let's plug the information of sigma B here and then rearrange the equation with respect to UB. That's why UB is equal to L1 elastic modulus and cross-section area and PC minus PB. So now let's plug all the numeric values into the places of PC and PB and L1 elastic modulus and A1. Then we can calculate the nodal displacement at point B, isn't it, right? And then let's put the information of nodal displacement UB into this equation. Then we can calculate the UC very easily. Okay? Then using UB and UC, you can finish the distribution of displacement. You can finish the distribution of displacement. So once I did this, then you have some distribution of displacement, U and X coordinate. Then using this information, the strain AB, strain BC, then you can plot the distribution of strain also. And then using this information of stress here, the stress, and also we can put distribution of stress, sigma. And by multiplying the cross-section area instead of stress, we can represent the information of nodal displacement, so internal forces, N. Do you have any questions? So here I'd like to take 10 minutes break. So we will resume the lecture in 12.